The ground begins to tremble.
Three,
Massive engines roars to life. We
two,
see clouds of smoke coming out of the exhaust.
one.
This is the most iconic audio we all would have heard before we send out our satellites to explore the vast universe. But have you ever wondered what amount of engineering goes into when a rocket lifts off? In today's episode, we are going to take a little peep into rockets science. Hi, welcome to Glitch, a podcast exploring tech news, how stuff works, innovation in our day to day technology, and the news surrounding them. I'm your host Vikram. I'm so excited that you are here. Thanks for joining with me today. Hey everyone, welcome to another episode of Glitch. I know I'm not regular with my episodes, and with a lot of things happening around me, I find very little time to record these episodes. But this is what I would love to do. These small sessions of podcasts help me to connect with my followers. And also, it's a great getaway from my routine. Hope you all are safe and taking care of your loved ones. I know it's a crazy time here in my country. There were a few people who reached out to me in comments and asking me about the situation here in India, and yeah, we have pretty hard time here. Things are getting better and we are working towards it. And thanks for your support. Let's get into today's topic. It's always an absolute beauty to watch a shuttle take off as the time goes T minus 0 seconds. At this time, the onboard computers check all the sensor data. They give the order to light the solid rocket boosters. In less than 1 second, the rocket achieves 6.6 million pounds of thrust, and the spacecraft takes off from its launch pad. No human pushes a button to make this happen. There is no astronaut sitting with a joystick to set the shuttle in orbit. It's an awesome display of power of computers and software doing its job in a well choreographed manner. But how much work does the software do? What makes this remarkable? By the time the shuttle achieves the escape velocity, there would have been billions and billions of sensor data flowing across 5 onboard computers. The onboard computer systems would have taken millions of decisions based on these data. Just to explain in detail on how these machines' computers work, let's take an example over here. 4 identical computers running identical softwares get real-time information from thousands of sensors. These make hundreds of millisecond decisions. A fifth computer with a different software stands by to take control if other 4 malfunction. Anyone who has witnessed a shuttle launch would have seen the dramatic belly roll the shuttle does soon after it clears a tower. It is the software which gives these orders to the gimbals in the main engines, and these gimbals execute this maneuver. It is the same software which keeps track of where the shuttle is, and based on this, it orders the solid boosters to fall away, makes minor course corrections, and after about 10 minutes, this directs the shuttle into the higher orbit. Even the smallest error in the space can have enormous consequences. The orbiting space shuttle travels at 17,500 miles per hour. A bug that causes a timing problem of just 2/3 of a second puts the space shuttle 3 miles off the course. If you are an engineer or someone who has a little experience in designing electronic systems, by this time you should have been blown away with all the design and planning that has gone through such a detail. What makes this remarkable is how well this software works. This software never crashes, it never needs to be rebooted. It's bug free. I feel like I'm explaining the first sight of Superman in movies. I was able to pull out this information. The last 3 versions of the program, each 4,20,000 lines long, had just one error each. The last 11 version of the software had a total of 17 errors. Just to give a comparison of a commercial program of equivalent complexity would have easily 5,000 errors. This software is perfect as human beings would have achieved. In the history of human technology, nothing has become as essential and as fast as a software. Software is everything, but it also sucks. What we have right now is like pre-Sumerian civilization. The way we build software is still in the hunter-gatherer stage. It's primitive. We supposedly teach computer science, but there is no science at all. So how do people working with such an engineering marvel manage to write a bug-free code? Well, Houston, we have a problem may sound good for a movie. It is no way to write a software in such scenarios. But how do they write the right stuff? It's the process. The group's most important creation is not the perfect software they write, it's the process they have invented that writes the perfect software. I mean, this explains everything which is going wrong in the commercial software environment. I feel that it's the process that allows them to live normal lives, to set deadlines they can meet, to stay on budget, to deliver a software that actually does exactly what it promises. It is a process that defines what these coders know. It is the same benchmark that everyone else in the software world is aiming for. It is a process that offers a template for any creative enterprise that's looking for a method to produce consistent and consistently improving quality. I'm insisting so much on this process because it's the beauty where we see such engineering marvels happen. To put it in simple terms, these processes can be reduced into four parts. The first part being the product is only as good as the plan for the product. I feel about one third of the process of writing a software happened before anyone writes a line of code. Nothing in the specs should be changed without agreement and understanding from both the sides. And no coder changes a single line of code without specs carefully outlining these changes. Most organizations launch into even bigger projects without planning what the software must do in blueprint like detail. So, after coders have already started working in a program, the customer is busy changing its design. The result is chaotic. Costly programming is where the code is consistently being changed and infected with errors even as it being designed itself. So all boils down to planning before even you executing a single line of code. The second one being the best teamwork is a healthy rivalry between the coders. The people who sit and write the code and the verifiers, the people who try to find the flaws in the code. We call them developers and testers. I know it's a two different world out there, but the healthy rivalry between these two departments will make a great code and great product for the customer. The third point being the database of the software. The database is your software base. So there is software and then there are databases beneath the software. One is the history of the code itself, showing every time it was changed, why it was changed, when it was changed, and what was the purpose of change. Next comes the error database, where you record what were the errors were, how the error managed to slip past the filters set up by every stage to catch these errors. Why wasn't it caught during the design or during development inspections or during verification? Finally, the database records how the error was corrected and whether the similar errors might have slipped through same holes. Now fourth, I feel that's the most important part. People here, they don't just fix mistakes. They fix whatever permitted these mistakes in the first place. The process assumes the blame here. It is a process that analyzes and discovers why the error got through. At the same time, I feel accountability is a team concept. No one person should ever be solely responsible for writing or inspecting a code. I think you should not get punished for making errors. If it was a mistake and others review the work, then you're not alone. I know I ended up talking everything technical and more deeper into the software process, which for a general audience might sound overwhelming, but I feel there is no point in talking about an issue without talking about its solution. But the real mind-blown moment is not realizing all the things I said now. It is when you think about SpaceX Falcon 9. It not only does launch the spacecraft in orbit, it also gets back the solid boosters so that it can be reused. I so want to talk about SpaceX's Autonomous Spaceport Drone Ships, ASDS, and its reusable boosters. This is actual beauty of embedded systems and rocket science in action. But we'll hold on for another episode. Until then, it's goodbye from Vikram. Be safe, take care, and ciao.